This video is on the common ion effect, and it's the continuation of the solubility equilibrium packet. So we've just talked about what the solubility product constant, or KSP, is. We talked about how to calculate KSP, and also how to calculate molar solubility. That was the first part of this section. So this second section is something called the common ion effect, and the name suggests that it has something to do with there being common ions, okay? Just like the name says. So, the first part of this, the first statement right here, okay, is a pretty bold statement. This is that the solubility of a slightly soluble salt is decreased by the presence of a second solute that contains a common ion. Okay, so that's like a takeaway, kind of a bold statement, something that's always true. And so then this discussion is going to be on actually kind of proving that, okay, with the math behind proving that the solubility is decreased if there's a common ion. So for example, calcium fluoride in equilibrium with its ions, okay? And so if you were to introduce a second solute, a second substance, one that either had calcium, like it could be anything, calcium nitrate or calcium chloride or anything, or you were to introduce something that had the fluorine ion, so lithium fluoride or potassium fluoride or something, okay? The presence of any one of those things that just mentioned from some additional source, okay, because what will happen is any of those sources of that common ion, okay, will increase the concentration of one of my products, which will disrupt the equilibrium. And then we know from Le Chatelier's principle in shifting equilibrium that if I have too much of these, it's going to shift equilibrium to the left, causing the solubility of this to be decreased. Okay, so that's what this bottom part says, that the presence of either calcium or fluoride ion from any additional source will shift the equilibrium to the left, and thus will reduce the molar solubility of the calcium fluoride. Okay, so the next thing we're going to do is kind of prove this to be true. So we're going to do two things. We're first going to actually solve for the molar solubility instead of me just like telling you what it is. And then we're going to solve for it in the presence of a common ion. So I'll do kind of like part A, part B. So we'll do molar solubility of CaF2. Okay. We can look up the KSP. We find that the KSP is 3.9 times 10 to the negative 11 for this substance. So I can write, what I just had up here. I want to solve for this molar solubility, so I'm going to call the calcium ion concentration X, the fluoride ion concentration 2X. I'm going to write a KSP, which would be the calcium times the fluorine squared. I'm going to plug those X's into this, so calcium was the X, the fluoride was the 2X, the quantity squared, right? This is not the first time we've seen that, 2X squared is 4X squared times X is 4X cubed. It's a very common, thing in these KSP problems. We know KSP, it's right there, equal to 4X cubed, so we're going to divide by 4 and take the cube root on the calculator, which I did all in one fell swoop here, so to speak. And I got the molar solubility to be 2.14 times 10 to the negative 4th molar. Okay, so of course, meaning, remember that was the X value, which is a 1-to-1 relationship. So meaning 2.14 times 10 to the negative 4th molar, or 2.14 times 10 to the negative 4th moles of this per liter of solution. So that's not a whole lot. We already expect these numbers to be small because they're slightly soluble salts, remember, keep in mind. So now what we're going to do is calculate the molar solubility, and I'm going to write that number up here, just so we can see we're going to compare. Okay, now we want to calculate the molar solubility when there's something else added. Okay, so this time I'm going to do the so let's change this. It's going to be like problem B. So the molar solubility of CaF2 in 0.01 molar of NaF. Okay, so of course the common ion is the fluorine, right? And so we're going to kind of go about this the same way. We're going to write the equilibrium, right? We know we're going to solve for the molar solubility, so we know we're looking for this. But in this case, the problem becomes a little bit like an ice chart. Okay, because I'm starting with some initial F minus, right? Before this process has even happened, before I have put the calcium fluoride in the sodium fluoride, I have some some F minus from this thing. Okay, now, keeping in mind that an ice chart really only discusses the things that are important in a solubility expression, so I'm going to kind of X out through this, because remember, it's a solid. We don't really care. It's not part of the KSP, so it's not going to affect our values here. So initially, I have no calcium in my solution, because initially it's just sodium fluoride, okay, but I do have some fluorine, right? The 0.01 molar of the NaF gives me 0.01 molar of the Na, which doesn't really matter, but it also gives me 0.01 molar of the F minus. Okay, so of course, these numbers are going to increase as this equilibrium is established. So this is going to increase by X. This is going to increase by 2X, right, because of the 2. And just like an ice chart before, we're going to add these up. 0 plus X is X. And this is going to be 0.01 plus 2X. Okay, so now I'm going to take these numbers and plug them into a KSP expression. So we've already written what we just did. We wrote a KSP expression just a minute ago. Okay, now if I plug these into here as is, it gets really ugly. There's a quadratic term. Oh my goodness, you have to solve it with the quadratic. But there's a shortcut, and the shortcut is this, and this works every time. Okay, in this idea of the common ion, okay, remember that this equilibrium that's established is very small, because the ionization that happens here, the solubility that happens, is very small. We're not getting a lot of calcium, and we're not getting a lot of fluorine. So what we do is we make an assumption that the value of X, okay, in this case, what's being added to the 0.01 is going to be really small. And so 0.01 plus 2 times a really, really small number is going to be approximately equal just to 0.01. And I know that seems a little bit weird, because you're kind of like, well, then what's the point of the 2x? Well, the point is it's going to increase by a little bit, but it's so minor that it's hardly going to affect anything. Now, plugging in my X for my calcium and just my 0.01 for my fluorine concentration, I no longer have this issue. See, I know KSP. I no longer have an issue of a quadratic equation or anything like that happening, and it makes this so much easier. So this is going to be 0.0001 X once I square that term. And then, of course, I just divide to find X. So actually the math, oops, I missed a 0. The math's pretty simple. So X ends up being, let's see, 3.9 times 10 to the negative 7 molar, okay? Remember, X in this case is still the same idea. X is the molar solubility, right? Remember, it's X, but it relates back here to the whole compound because of the one-to-one relationship. So remember before, so what's the whole point of this, right? The point was to prove that a common ion would reduce the molar solubility, and in fact, it very much does. Initially, the molar solubility was on order of 10 to the negative 4th, and with the addition of a common ion, the molar solubility is on order of 10 to the negative 7, right? That's what is that, 10 to the 3rd? That's 1,000, isn't that 1,000? 1,000 times less soluble with that common ion, okay? So essentially, we just proved that the common ion does, in fact, decrease the solubility. So there are 2 practice problems. We'll do those quickly, and then that's where this video will stop. So they're very similar to what we just did. All right, so practice problem 1 says the KSP of silver bromide is given to us. So let's see, it's 5.0 times 10 to the negative 13th. Okay. What's the bromide ion concentration of a 1 liter saturated solution of silver bromide to which 0.02 moles of silver nitrate is added? So 0.02 moles of silver nitrate. Of course, in this case, our common ion is the silver, right? So I'm going to treat this like, I know it's going to be an ice chart. Anytime you have a common ion, it's an ice chart. Remember, I'm going to exempt this. So in this case, the bromine is not existent initially, and the silver is a 0.2 moles in 1 liter, so 0.02 molar. Of course, they're both going to increase by a factor of x this time, 1 to 1. So this is going to be 0.02 plus x. This is going to be x. Remember, we make our assumption that the x value is going to be really small relative to this number. So we say, it's close enough to 0.02. And then we write the KSP. We plug it in and we solve. So KSP was silver times the bromine. Let's see, KSP is up there, 5.0 times 10 to the negative 13. This is, silver is being represented by 0.02, sorry. Bromine's being represented by the quantity x. So all I have to do here is divide by 0.02. And I end up with, let's see, again, I don't have a calculator, but I did this before. I end up with a value of 2.5 times 10 to the negative 11th molar, which is the value of x. And if you go back and revisit your question, the question said, what's the bromide ion concentration, which is what x was. So there you go. In this case, with the common ion of silver, the bromine, concentration is 2.5 times 10 to the negative 11th molar, pretty small, which we would expect it to be. And then the second common ion question in this packet says, what's the concentration of the sulfide ion in a 1 liter solution of iron 2 sulfide? To which 0.04 moles of iron 2 nitrate, I guess I should say, is added. The KSP of iron sulfide is 8 times 10 to the negative 19. Wow, that's a small KSP. All right, so common ion is iron. Right, so ice chart. So there's no sulfur to start with, right? When I'm just looking at this solution, there's no sulfur, but there is 0.04 moles in a 1 liter container, so 0.04 molar. Of course, these are both going to increase, and they're both 1 to 1. So this is, again, it's going to be an easy one because it's just x and x. So 0.04 plus x, x. Make my assumption that x is really small in relation to this number, right? Notice I don't get rid of it here. We're saying it's just really small in relation to that number. So this value goes to approximately 0.04. I write my KSP, and I solve. And that's it. Common ion problems are pretty simple. 8 times 10 to the negative 19th equals 0.04 times the quantity x, right? Divide by 0.04, and we'll get x, which is in fact the molar solubility of the sulfide, which is what the question asked me for. Once I do this math, it's 2 times 10 to the negative 17th molar, and I have answered my question. So that is common ion, keeping in mind that the important takeaway is that a common ion will always decrease the molar solubility of the compound that you're studying.